Welcome to qnawire.
This is problem 26, chapter 23. In this problem, we're asked to derive the expression for the first order dark fringe for single slit diffraction. So let's go ahead and draw our single slit. Let's draw it wide enough because we're gonna so this is a zoomed in version of the slit. Here we're extremely zoomed in. We're gonna have the screen located much further than the slit is wide. Okay, so here, even though I'm putting it relatively close, in reality the screen is going to be much further. This distance from the slit to the screen is going to be much further than the width of this slit. So here the width is, we could call it W, and the distance between this slit and the screen is going to be L. This drawing is definitely not to scale. The main idea here is that the order of L is much greater than that of W. Okay, so having stated that, once you shine light onto a single slit, you observe a diffraction. You observe this interference pattern, single slit interference pattern here, due to the diffraction of the wavelets along the opening here. So as light is coming in to the slit, here let's go ahead and draw it in red. Here you have light coming into the slit like so. And according to Huygens principle, you have these wavelets like so here at every point here that combine form this overall crest here. By the time they get here, each one of these wavelets continues to diffract. So here you have the wavelets here. They're going to continue to diffract, and that's what's going to, their interference, constructive and destructive, is what's going to cause the diffraction pattern here. So we observe a diffraction, an interference pattern here, where we have this maximum bright spot at the center of the screen. So let's go ahead and graphically represent that by a huge peak here. And then we're going to have a series of much smaller peaks, like so. So this is the interference pattern that we would observe. The distance between the peak and the screen represents intensity. So in reality, what you would see is, so if you're looking at the screen, you would see an intense initial dot and a bunch of, and then a series of smaller ones. So a series of smaller dots on either side. So dots here, like that, like so. So this is the interference pattern for single slit diffraction here. The question is, why does this occur? So, like I said, with Huygens principle, you have these wavelets here that combine to form this crest. Now let's go ahead and treat each of those wavelets as a light ray. So let's draw a couple of them. Let's draw 6, let's say. Also notice that you're going to have this huge peak here at the beginning, and then it's going to drop off, and then you're going to have this first dark fringe. This is what we're asked to solve for. So if we draw a line from the center of the slit to the screen where that maximum occurs, and we draw another line from the center of the slit to that first order dark fringe, we're going to define this angle as theta. Okay, now let's return to the slit itself. Let's go ahead and draw some of the wavelets as light rays. So here let's draw around 6. So 1, 2, 3, 4, 5, 6. Now let me align them. So as the wavelets go through the slit, they're going to be here evenly spaced. 2, 3. So I didn't space them adequately, so let me go ahead and move this down here. I want that one to be there. I want this one to be somewhere around here. I want this one to be here, like this. So what I'm doing now is I'm trying to evenly space them. Okay, and the reason I chose 6 is because it's an even number, and that's going to be important for this next step. So let's go ahead and number these wavelets. We're going to have like 1, 2, 3, 4, 5, 6, and like I said, we're picking an even number of them so that this wave this light ray from this first wavelength, I'm going to go ahead and pair it with this fourth one here. So I'm going to pair this first wavelet with this fourth one, and if I do that, then I can pair the second one with the fifth one, and then the sixth ray, the third and sixth one are going to get paired together. Okay, so we're talking about the angle to that first order dark fringe. So what is the path length difference between this first ray and the fourth one? So let's go ahead and draw a perpendicular line from this first ray to the fourth one, and this is what we get. Our hypotenuse, let me go ahead and draw it in blue. Our hypotenuse would be this. Here a triangle is formed. Here's our hypotenuse, and we're going to call this angle between the blue line and the green line theta. So according to that, we see that sine of theta is going to be equal to opposite, which is the path length difference. Let's call that delta, over the hypotenuse. Now here, the hypotenuse in blue is half the slit width. So let's go ahead and write that as W divided by 2. Let's move this term, W divided by 2, to the left-hand side. So we have W divided by 2 times sine theta is going to be equal to delta, where delta is the path length difference. We're interested here in the destructive interference caused on the screen, this first order destructive interference. For destructive interference, the path length difference must be equal to an odd integer multiple of half wavelength. So here m is going to be equal to 1, 3, 5, etc. Here, for m is equal to 1, because it's going to be the first order diffraction. So here, let's go ahead and plug everything in for m. We have W divided by 2 times sine of theta 1 is going to be equal to 1 times lambda over 2. Let's go ahead and multiply both sides by 2, and then we get the expression that we wanted to, which was W times sine of theta is going to be equal to lambda. So this is the expression which describes the angle associated with that first order dark fringe. We didn't look at the other light rays, but notice that if we pair this second one, let me go ahead and label it. This second one, this second light ray, with this fifth one, notice that if we draw a perpendicular line, let me go ahead and draw this in light green, from 2 to 5, notice that this is precisely the same length as this dark green line. And here, if I go from 2 to 5 here, that is also W over 2. So in pairs, 2 and 5 destructively interfere at the same point in the same way that 1 and 4 destructively interfere at the same point. So you could imagine a bunch of wavelengths, and we choose an even number of wavelengths so that they could pair off in this way. Otherwise, we're going to have one remaining one. And we don't observe any light here, so they all must cancel out in some way, and this is how they do it. So here, we're going to see that this distance between 2 and 5 is precisely the same as the distance between 1 and 4, and so on. So we could also pair 3 and 6, and it's going to be exactly the same setup here with the angles. So sine of theta is going to be that path length difference over W over 2, because the hypotenuse is just being shifted as we go down. So we start off with 1 and 4, then 2 and 5, and then finally 3 and 6. So notice you could do the same thing if you did 8 light rays instead of 6. Here we just did 6. But either way, you're going to arrive at the same equation. W sine of theta 1 is equal to lambda. This is the angle for the first order dark fringe for single slit interference.